So we're going to begin by dragging the CFX module into the workspace and right-clicking on geometry and opening a new Design Modeller geometry. Just select the positive x-axis and view the YZ plane. And we're going to make our shell only 0.3 meters wide, so if you just zoom in and you can scale the bar at the bottom until it's about 0.4 meters long. So selecting the YZ axis, selecting sketching and selecting circle. Now if you create that circle about the origin, so if you just hover there and it should become a P, so just holding your left mouse button down and dragging, and then assign a dimension, and that's called D1. So if we view here, I can just change that to be 0.3 meters. We can then extrude that to be 0.5 meters long. So select extrude. There's only one sketch available, which is sketch 1. If we add material and make it 0.5 meters, just select generate. You can rotate and now see that that's been created. What we're going to do is create the in and out flow to the shell. So that will be a tube coming in here vertically and a tube leaving here vertically. So we can create those simply just by selecting the Z axis and selecting, in this case, the XY plane, and I want my inflow to come through a circular pipe. So if we take that, just zoom in slightly, just make a circle that's coincident with the axis. And now we can decide what dimension or what diameter we want that to have, but also how far it is from this axis here. So what we can do is apply a constraint between the centre of the circle and this axis here. So that's currently 3 centimeters, so if we leave that as 3 centimeters and then make this also 3 centimeters away, just rotate it to make sure that seems appropriate. And we're just going to expand that out to 4 centimeters. So let's just have a look again from the top. Right, so I'm now going to extrude that. So we extrude this sketch, sketch 2, and I'm going to add material to be 0.2 meters. So if we just rotate, you should be able to see the top of it just protruding there. And if we select generate, you'll see that the inflow shaft now exits out the shell. We can repeat this process in a similar manner for the outflow. So just now selecting the negative Z. And we now want to create our circle on this side. We want to create a circle in a similar position at the opposite end, but we then want to extrude it in the negative Z direction. So again, selecting the XY plane, but selecting a new sketch. So this will be sketch 3. Creating our circle that's coincident with this axis. and again making sure that it's got an appropriate diameter, and then also that it's an appropriate distance from the edge. So at the moment we are unable to select the edge of this circle here, but if we know that this is, then we know that distance here between this axis and here will then need to be 0.47 meters. So I'm just going to change this to 0.4, and this just needs to be 0.47, and it'll put it in the similar position to that shown here. The direction of extrusion needs to be in the negative Z. So I'll select extrude, and I'm going to assume it's going to pick up sketch 3, and it has done. Then here where it says normal, we want that to be reversed, and you can see the preview just sits out at the bottom here. So just select generate, and now we've got the geometry for our shell. So I strongly recommend saving at this point. So just select Save Project. So what we're going to do now is create tubes and a fluid within those tubes that pass through this shell, thus making it a shell and tube heat exchanger. So just selecting -X and zooming right in, I'm going to select the YZ plane because that's where we're going to be sketching. So selecting this plane and creating a new sketch. So I'm going to begin by creating a circle, and I'm going to do it on the Z axis, and you see it just drags out, and I'm just going to apply some dimensions. So I'm going to make that as large as 2 centimeters. I'm then going to extrude this. So just selecting extrude, and selecting sketch 4. Rather than adding material, I'm actually going to add a frozen geometry. We're going to extrude that for the entire length of the domain. So that now should go all the way around and reach this exit here. Just going to perform the generation. And although it's come through slightly dull, you can see that there's a fluid geometry just here. So we can repeat this process, and this time we can create the tube that surrounds this fluid. So just applying another sketch, again on this YZ plane. This time it will be sketch 5. And we're again going to create a shape, but this time we're going to create a circle that's coincident with that diameter, but then also has a second shape here. So we're going to extrude between this circle, and that's going to make our pipe geometry. So just selecting extrude, and rather than applying material again, adding in a frozen geometry, keeping it to that 0.5 meters, If you've done it correctly, you'll see another region of a slightly different colour to the main shell and that fluid. Before we go any further, we're going to have a lot of fluid and solid domains involved in this problem. So I'm going to recommend that you just name your different regions here. So the solid region that's called solid, I'm just going to rename that and call it shell. And rather than being a solid region, it's going to be a fluid region. This next region here, I'm going to call tube fluid. And then this final region here, I'm going to call it tube solid. So this is the metal that's standing between the fluid passing through here and the fluid passing across and over the shell. And that's going to remain as a solid. So we should have shell, which is fluid, tube fluid, which should also be a fluid, and then tube solid, which should be a solid. So the next thing we need to do is create multiple of these, because in a shell and tube heat exchanger you wouldn't just have one tube passing through, you would have a collection of tubes. So I'm going to create a pattern. So create, and then pattern operation here. I'm going to change it from linear to a circular pattern. I'm going to select the tube fluid and the tube solid for this. So just that one. Hold control down, and then that one as well. The next bit is we need to actually select the axis that this is going to be rotating around. So the axis should be visible here. And sometimes you might not be able to see the axis, and if you can't, that's okay. Just select one of these sketching options that mean you can. If I select the XY plane, the axis should be visible here. So there you go, I've now managed to select that axis. And it says how many copies do I want. If I have 6, then I want 5 copies of the original. So just viewing from the end and zooming in and selecting generate, should be able to see them all the way around. And of course, this is quite a low number of tubes for a shell and tube heat exchanger. I'm just doing it to save computational time and to demonstrate the process. So you might have multiple rings, and that's okay, but for this case, this is all we're going to do. So again, please do save. You never know when software will crash. It's always worth doing. So the next operation we're going to perform is a Boolean operation, which will separate this shell domain from our tube fluid and our tube solids. So if you just select create and then Boolean, we're going to select subtract. So our target body is the shell, and then our tool body is this collection of bodies in here. So the best way to do this with this many bodies is just to select them from the tree here. So it's asking us if we want to preserve the tool bodies. So the tools are obviously the 12 things we've just selected. If we were to not preserve them, then they would disappear and we'd have no fluid regions or fluid solid regions. So we need to make sure that they are preserved. And if we just select generate, you might notice that some of these don't look like they're visible. They are actually It's just the way the software is displaying them. So now we should have a shell domain, but also have fluids passing through it, which are hidden from the shell by using the tube domain, so the tube solid domain. So once you're happy with that, just shut down Design Modeller and then double click on Mesh and let that open. So now that your geometry has imported into the meshing software, if we just begin by generating a default mesh and seeing what this produces, you'll notice in the bottom left hand corner that it talks about meshing different parts, and obviously there are so many parts that the software needs to mesh. So by default we've got something that looks like this, which we can rotate and zoom in slightly, and immediate deficiencies come to mind. So immediately there's no prism layer cells on the inside and the outside of these tubes, and there's only one cell across the tube, across the diameter of the tube. I'm just going to allow this the first time round, just so we can get this set up, get it run quickly. We'll go back and correct this later on and optimize the mesh, and you'll see the difference that that has on heat exchange. So one thing I would like to highlight is this connections option here. If you just open that up and open up contacts, what you'll see is different regions that are connected to one another by interfaces. So what this means is, let's take this top shape for example. The fluid passing through the tube, the heat transfer information needs to go from that fluid to the tube, but also the heat information from the tube needs to go to the fluid inside the shell. So we actually have two different interfaces there just for that particular tube arrangement. So we have in total 12 interfaces, and this is why these simulations take so long to run, is because there's a lot of information being passed between each domain for the solver. So I'm going to shut this and move on to setting this case up in Ansys CFX. So just right clicking on Mesh and selecting Update, and then once that's done, just double click on Setup. So I'm going to begin by creating several domains. So I'm going to treat all of the fluids passing through all of the tubes as one domain. Then I'm going to treat all the tubes, so all the metal parts, I'm going to treat those all as one domain, and then I'm going to treat the shell as one domain as well. So we can create a new domain by selecting domain at the top. So I'm just going to call that shell. And we're going to begin by selecting its location. And because these are not named, that's absolutely fine. We can just scroll through and you'll notice that, of course, it's that one. Just be careful to specify that it actually is a fluid domain. And then I'm just going to delete and call this fluid water and select it from this library here as water. I'm going to assume there's no buoyancy effects here because we're going to be running the fluid through it so fast. And we're going to change the heat transfer model to be thermal energy. And I'm just going to leave the turbulence model as k epsilon for now. So that's one domain setup, and you'll notice that a interface has already assigned itself to that domain. So I'm going to select our next fluid domain. So if we go to domain, I'm going to call it tube metal. And the easiest way to do this is actually just to select everything. And what you can do is just untick the things that aren't metal. So I'm just going to go through each one of these. So if we tick this one off, it's obviously a fluid. If we tick this one off, it's not a fluid. If we tick this one off, it's a fluid at the bottom left. And that's not a fluid. And that one's a fluid. That one's not. That one is. That one's the shell. That one's not a fluid. That one is. And then we should be looking for just one more, which is that one there. So that means those 6 selected are just sitting under these details here. They have the property of the metal. So just selecting OK and selecting solid domain, and I'm just going to change the material to be copper, and we're not assuming any motion, we're not assuming any mesh deformation, but we are assuming thermal energy, and to save computational time we're not assuming any thermal radiation. So finally, that just leaves us with the domain that we can call tube fluid. And if we just double click on tube fluid, you'll notice that water's flowing through it, that it's thermal energy, and we're using the k epsilon model. Again, I'm just using these as defaults for the moment. They can be changed and should be changed, but we just want to ensure that we have something set up that we can run, then we can optimize it later. So just rotating and viewing from the negative x direction, I'm going to start by creating boundary conditions. So if we just view the top of the shell here, I'm going to begin by creating a boundary condition that gives us the flow in here. So if we go to shell, right click, insert boundary, and create a boundary called shell in, and it's an inlet, and it's going to be that surface there. And I'm going to create a mass flow rate of 5 kilograms per second passing through. And this is going to have a static temperature of 5 degrees Celsius. And I'm just going to apply that. So what we need to do next is rotate and select an outflow condition here. So right clicking on shell, insert boundary, just select an outlet. And that's going to be here. All we need to do is specify the relative pressure across that surface. So in this case I'm assuming that there's no pressure drop right across that boundary, which there shouldn't be any significant drop there. So this surface here, I'm just going to rename it and call it outer wall. And that's all it is. It's just a surface that contains the fluid that goes through the shell. And in this instance, I'm going to assume it's adiabatic. Of course, there are other options here. I'm going to assume adiabatic operation for the moment. In terms of your tube fluid, we're going to have to specify fluid passing through there. In this case, I'm going to assume that flow is moving in opposite directions between the shell and the tubes. So I'm going to create my inlets on these surfaces here. So just right clicking on tube, insert boundary, I'm going to call it tube inlet. And if we just select each one of those, just holding control down in each case, and we want to specify a mass flow rate of, let's say, 1 kilogram per second. And we're going to assume that the flow comes in here at 99 degrees Celsius. So we can select apply and then just rotate and now create outlet boundary conditions for the outlets of those tubes. So just right clicking again, boundary, and then outlet. Select an outlet condition and then select each one of these. So again, just holding down control. And then go into boundary details, and you should just need to select an average static pressure. And there's one more thing we need to do. If you right click on Solver and just insert an expert parameters, if you go to the convergence control tab in expert parameters, if you just select check isolated regions and set that to false, because sometimes the solver reads these as regions that's not having the information pass between one another, which is of course not true in this case because we have interfaces for each different domain. So just double clicking on solver control, and of course we'd normally modify these, but just to ensure that we get the simulation set up initially, I'm just going to apply that. And don't forget to save. And then once that's done, shut down CFX Pre and double click on Solution to open up Solver Manager. Okay, so just select Dual Precision, and I'm going to run this initially in serial, so this just means on one processor because I haven't refined the mesh yet. When I do refine the mesh, of course that will be changing, and just select Start Run, and we'll just monitor and see if there are any error messages that come up. If they are, we'll investigate them and deal with them, otherwise we'll let the simulation run to completion. So our simulation is on its way to converging, but because this is only a demonstration case, I'm just going to stop this a little bit early. In this tutorial, all I want to do is demonstrate how we do some basic post-processing of this. and show that it works. So if we just shut down the solution element, give it a moment to catch up, and then open results. So because this is just a introduction to the shell and tube heat exchanger, I'm going to just do the most simple type of analysis that we can, and just select location and create a plane, and I'm going to create that plane on the ZX plane at the middle. So we're just going to be cutting through our inflows right the way through the shell, but of course that means slicing the tube fluid and tube metal as well. So just selecting the colour, and let's just change that to temperature, and select a range that's local to this plane that I've just cut. So you can just see the temperature distribution along that plane. So what you should immediately notice is that the temperature in the shell region does increase from approximately 278 Kelvin all the way up to about 320, 325. If we zoom into the region of fluid that passes through the tube, you can see that only minor cooling actually occurs. And of course that's an implication of the coarseness of the mesh. And if we zoom in, for example, at this region here, this head is going to be the tube, and this is going to be the fluid within the tube. So even though there's some heat transfer, it's very, very limited. In the next tutorial, we're going to apply some equations so we can determine the overall heat transfer coefficient of this shell and tube heat exchanger.